Okay, so let's take a look at the cogroup command. So we've seen the group command, which we're showing a single data set, and the cogroup command does the same thing on multiple data sets. And we've seen this mechanism before when we talked about MapReduce, but here in Pig we make this operation explicit and give it a specific command, and we'll try to see why that is. Okay, so the syntax looks like this. You say cogroup a data set by some field reference or multiple fields. And here we're referring to a field by name, and here we're referring to a field by position, as we've seen before. And so if this is A, a bag of tuples, and this is B, a bag of tuples, then the cogroup of them looks like this. So now we have a group field, and we have a data set A, a field named A, and we have a field named B. All right, so we still have the same grouping key, but we have two groups associated with it, one from one data set and one from the other. Okay. So a couple things to point out. One is if there are no tuples from one of the data sets, then it just gets the empty group. And here you see an example from B. And then the other thing to point out is this is a little different than what happens in MapReduce directly, where what we showed with the join operator with MapReduce is that you could use the join key to sort of co-group two relations, and then all of these tuples would all sort of appear in the same group in the reducer. But here we sort of make it explicit to make it two separate groups. Okay. Fine. So I want to come back to cogroup in a second, but first let's talk about another operator which is just called join, and so it does exactly what you'd expect. So join, you say join A by some set of field references and B by some other set of field references. Okay, and given A and given B, the result will be what we've talked about in the past, which is you look for the first position of A, $0, and find all the corresponding first positions of B. So here's 1 and 1. So we have 1, 2 from A, and 3, 1, 3 from B. Okay. So there's nothing stopping you from having multiple data sets out here. As many as you want, and they can all be sort of processed together. And so you can think about what's going on here is that this is one MapReduce job underneath the sheets, where in the map phase, every tuple from a variety of data sets is all being associated with the join key, represented by this field reference in the syntax, and then shuffled across the network to arrive at the reduce phase. Okay, so here's what it looks like. Well, if we have multiple relations represented by colors here, green, blue, and red, well, they can all be processed by the map phase and associated with keys, shuffled across the network to produce the join tuples here. Right, so there's nothing fundamentally binary about this operator. Right, it's just processing tuples associated with the respective join keys and shuffling them all across the network. What can go wrong with this basic mechanism of associating tuples with the join key, shuffling them across the network, and then computing the join on the reduce side, which is what we did in the assignment as well? Well, so one example might be if one table is very, very large and the other table is very, very small, there's an opportunity to do something much, much faster, which is replicate the small table across all partitions of the large table, which allows you to do all the work in the map phase. Okay. The second sort of special case here is a skewed join. What I mean by that is if there are many values in one table that join with many, many, many values in this second table, then you'll end up with one reducer doing most of the work, and the effects of parallelism get sort of washed out. And the third special case algorithm is to do a merge join. And so this takes advantage of the fact that you may have already grouped two relations in the same way, such that you know for sure that on a single machine, I've got all the tuples I need from one relation and all the tuples I need from the other relation. Okay, so let me see if I can make this more clear in pictures in the next few slides. Okay, so for a replicated join, the situation is we have one large table broken into pieces and one much smaller table. And so what we could do is just shuffle all these tuples across the network and do the join in the reduce side as we do normally. But there's an opportunity here that says, well, look, if this thing is small enough to fit in memory on a single machine, why don't we just copy it, send it out there to every map function that wakes up, we'll go pull it across the network directly. Okay. Then we have all the information we need right here in the map side. Every one of these tuples can be joined with corresponding tuples in this partition. Every one of these tuples can be joined with corresponding tuples in this partition, and so on. And so at the end of the map phase, you end up with the right answer, all the joined tuples for this sort of blue A and this red B. Okay. And so why is this cheaper? Well, we didn't have to shuffle everything across the network. We did it all in the map phase, and it makes a huge difference. Okay. So you might see this called a broadcast join as well. So the small relation must fit in memory, and the idea is that each mapper in the map function pulls a copy of the small relation directly out of HDFS. Okay. All right, so for the skew join, the situation is as usual. You got two relations, this sort of blue one and this red one, and the map phase associates each tuple with its join key. But the problem is that most of the data ends up on a single reducer, and the reason is because maybe most of the data here is associated with a single join key. Okay, so for example, if you're joining on order ID and line item, you're trying to associate all line items with their corresponding order. It could be that one order had millions of parts and all the other orders had 5 parts or so. Okay. So if a significant fraction of the overall data set is associated with a single join key, then this reducer will be doing all the work, and there won't be much benefit to parallelism. Okay. So this would work, but there's a problem. So this is from a former student here at UW who did some work on this problem. And this plot shows time and seconds on this x-axis, and this is just a list of all the tasks. And so you see that the reduced tasks here, they can't start until all the map tasks are finished. Okay. And the map tasks mostly finish quite quickly, sort of maybe 20 seconds, but one or two of these map tasks take a very long time, sort of on the order of 270 seconds or so. Okay, so all this space in here is sort of wasted work. There's a couple of problems here. One is fundamentally a map reduce. In many applications, you logically actually could start doing some work early based on the map output that's already been finished, and that's just not the way map reduce is designed. You can't it's not designed to be able to take advantage of those applications because you can't guarantee that it's safe to do so. So for example, if you're adding up numbers, you could start adding up in the reduce phase, you could start adding up numbers early. But if you're doing something more complicated, you may actually need to wait for all the results to be present in order to get the correct result. And so since they can't guarantee that it's safe, they make you wait. Okay. So fine. So this skew problem ends up sort of killing parallelism and turns a job that could take sort of 50 seconds into one that takes 350 seconds. And it's not even significantly longer than doing this sequentially. If you sort of added all these pieces up, well, I shouldn't say that. This is still worse in sequential, but you certainly lose a lot of your bandwidth in parallelism. Okay. So one task might take 5 times as longer than the average, and so there's a little benefit. And so one takeaway here, so I'll tell you what one way to partially solve this problem on the next slide, but the takeaway here is if someone asks you what the one of the biggest performance bottlenecks of MapReduce is, you should say stragglers or skew. Skew is more of a term for this in the database community, but stragglers is maybe a little bit more common. Okay, so this is a straggler task that takes a lot longer. All right, so what can we do about this? Well, here's the situation where we had a lot of keys that all ended up on the same reducer, and this guy's taking too long. One thing we can do is split this data up into more reducers. So allocate a few more reduced tasks and move that data over here and split it into 3 more. Now, broadcast that little red relation, right? So I made it disappear from over here, recognizing that this is perhaps small, and replicate it to all 3 of these reducers. So it's sort of a combination of the replicated or broadcast join and the regular reduce side hash join. Okay. So now you've got 3 reducers working on this problem as opposed to just one, and you get things a little bit more balanced. And so this skew join is something that Pig can do if you specify it. All right, it won't do it automatically though. So fine, and so now we get our entire joined relation, which is what we want. So finally, merge join is the third special case. And this is, let's see, so the first special case was an opportunity to do things much faster if one relation was very large and the other relation was small enough to fit in memory. Skew join is more of there's a problem that can occur and you need a special trick to be able to address the problem. Merge join is more like the former. It's looking at an opportunity to use a more high performance algorithm when certain conditions are met. And so what are those conditions? Well, when you recognize that the red relation and the blue relation are already been co-partitioned on the appropriate join key, right? Then the map phase alone has enough information to just compute the join itself. It doesn't actually need to assign it all to assign each tuple to a join key and shuffle it across the network, right? So you know that all the line items for a particular order, for every order that's here, all of its line items are also here on this machine. If you know that to be true, then you can do it in the map phase. Okay. So the question may be, when is that true? Well, that's when we go back to the cogroup operator. It's possible that you've already partitioned these two tables on the appropriate join key because of a previous command in Pig. Okay. And so it can be aware of that and use a merge join. Sorry, I say be aware of that. You still specify explicitly that you want to use a merge join, but so Pig's not doing that automatically, but you can take advantage of this situation when it arises. All right. So since each mapper already has local access to the records from both relations, they're already grouped and sorted by the join key, you can just read in both relations from disk in order and compute the join. All right. So we have this cogroup operation and we have join operation. Why do we need both? Well, the reason to make cogroup explicit is that if you think about it, join is really a two-step process, right? There's one step to create the groups based on the join key, and then a second step to actually produce the join tuples. But that group creation step is useful for a lot of applications, not just producing a join. So for example, if you want to cogroup and add up all the contributions from each relation, you can do that in a single step. You don't need to sort of join the tuples first, then do another grouping afterward, which is something you would have to do in relational databases. So that's a chance to take what would be 2 MapReduce jobs and combine them into just one. Okay. And so here, I guess the example is if you want to just count the tuples. Okay, so, but, what to point out here is that you can express join. Join is essentially just syntactic sugar. You can express a join in terms of cogroup. First step is to cogroup on the same column on the join columns, and the second is to run this for each command that would generate a flat view of results and revenue. Sorry, I guess I should say A and B here. That's sloppy. I changed the names. Okay. Fine. So other commands that we're not going to talk about in detail are store, which writes data out to HDFS, so it's available for future commands. Union, that combines 2 data sets together and removes duplicates. Cross product, which finds all possible pairs between 2 data sets, which can be useful if you're about to compute some sort of similarity function, as we talked about. And then dump, which prints output to the screen. And then order, which sorts the output. Okay. So as an example of store here, remember you can also, just like you can use your own custom function to parse data, you can also use your own custom function to write it out. Okay, which means it allows the data to be more compatible with, say, some other system that you're using, say MapReduce itself or some other application that expects data in a certain way. And so that's again, I sort of stress this with the load command as well, but this is actually pretty powerful and a pretty big difference from this, walled garden approach that relational databases take, where everything sort of goes in and then it's under complete control of the database. This sort of has more permeable boundaries where you can kind of have data lying around in whatever format, and you're still able to process it with Pig, but you can also process it with other systems as well. And so the reason this is crucially important is not just sort of a performance optimization for reduced load time or something. Although sometimes that can help as well. It's because this data is too big to move nowadays, right? You can't put it all in the database and then suck it all out and move it over to some other system for working with. It's just too big. You can't move a petabyte, right? You have to bring the computation to the data as opposed to bring the data to the computation. Okay, and so these abilities to work with in situ data, produce sort of in situ data is emerging as a sort of a key requirement in this big data era that was not such a key requirement in the sort of era of relational databases. Okay.